First of all, thanks. Thanks, Alberto. Thanks the whole organizer of the school. Hi, everyone. My name is Marco. I'm coming from Genova, and I work at the Jefferson Lab in hadron physics. But in the last, let's say, 10 years, I also shifted to LiDAR matter searches at accelerators. This is a kind of different flavor with respect to the standard hadronic physics, not only because the subject is different, but also the way and the attitude, the approach is different. We are using hadron physics to have a lot of phenomenology and, let's say, a lot of possible explanation of facts, of things that you measure. Here, in some sense, is the opposite. You have, a couple of observations, in particular dark matter, the one that comes from the sky, the one in the universe. You have some evidence, but it's very, very difficult to connect and attach to a model, let's say, to an explanation. Same thing, or even worse, if you look at the dark matter produced at accelerator. So let's say signal over beyond the standard model. This is, really, really tricky. So you have to rely mainly on theoretical background, on theory predictions. Theory predictions that are not based on phenomenology. Again, it's kind of different. This is not the scientific method. The scientific method is you have a phenomenon, whatever it is, and then you try to explain. Here, in some sense, is the opposite. You are trying to guess, to, let's say, think about a possibility, and then you shape your experiment in order to validate the hypothesis. That is, tricky and could be in some way, misleading. And there are people that are not, very happy with this approach. Actually, again, this is kind of weird, in particular for us, that we are coming from, again, a field like hadron physics, where you have a lot of measurement, a lot of observation, a lot of proofs of something, and then maybe the interpretation can be, controversial, can be complicated, but at least you start from a measurement. Here is the opposite. So this is just to give you kind of a warning that what I'm saying is strongly based on, let's say, theoretical ideas, and you will see that, unfortunately, so far, all these theoretical, all these models, all these ideas were not confirmed by experiments. So it's, needs to be taken with a little bit of, let's say, grain of salt, or anyway, a little bit, you have to use your criticism before, to buy whatever I'm trying to tell you. So I'm going to talk about LiDAR matter searches. In particular, I will focus on, okay. I will focus mainly on a fixed target experiment, and in particular for Jefferson Lab, I will show you, how many different experiments are planned or already ran here. So this is the outlook of these couple of hours. So the dark matter, first of all, I'm going to introduce it a little bit. Then in particular, a flavor of dark matter is a thermal dark matter. We'll see why it's important. And in particular, the LiDAR matter and the fifth fourth, so-called, let's say, the dark sector. Then I will focus on, try again to convince you that LiDAR matter makes sense to be studied at accelerators rather than, direct detection or a big experiment like xenon, like DarkSide, big experiment running in the caves. The experimental technique, in particular for a fixed target experiment, I'm not touching, I'm not going into details for experiment at colliders. That is another, in an entire field, because LHC, in particular, CERN, has invested a lot of money and is, running or wants to run several experiments with the proton collider. And then, again, trying to, going on a different technique, different way. Again, given the fact that there is no clear phenomenology, the field is completely open. And sometimes, the fact that it's so open may be a little bit scaring, or let's say confusing. But this, let's say, let the fantasy of both theoreticians and experimentalists completely, free, and then we can invent a different experiment, perform it in different ways. So there is a lot of variation of that, and so I think it deserves to just give you an idea. I'm not going to go in details in any of them. And then I will finish with, just again, try to convince you that this field is booming. So there's many of different plans and experiments planned for the future everywhere in the world. I mean, and the time scale for this experiment is not, few years, it's maybe a few tens of years. So it's something that, may be of your interest for your professional career. So let me start from the standard model of particle interaction. This is a very well established theory that works very well. If you think about, you get the G minus 2 for the electron with one part. I mean, you do a prevision, you have your Lagrangian, you calculate it, you calculate what is the value that you're expecting, you compare with the experiment, and you get a precision of 1 part over 10 to the 12. This is, is enormous. It's probably the highest precision ever reached by any measurement made by humankind. Similar things for length shift or, QCD is completely under control. But this is just to tell you that the standard model works. The standard model is based on different families of particles. It connects together, links together, particles and mediator of interaction. So it doesn't make any sense to speak only about particles of the standard model. You always need to consider the fields that are the electromagnetic, that are connected to the forces that we know, electromagnetic interaction, the strong interaction, the weak interaction. And if you look at here, there is, something missing. There is nothing connected to gravitational force that we don't know yet if this is, a normal force like the other 3 that we know, or it's completely, detached. People are trying to integrate a gravitational within the standard model, but this is pretty difficult, probably because the gravitational forces or the gravitational interaction is more about the entire space where we are, rather than, something on top of the space. It's something really deeply bounded to the way how you describe your environment in some way. And this may cause, difficulties, and it's a kind of special role. But anyway, so we know that there are 4 different forces. And again, the precision at which you make prediction using, not in QCD, we know very well that QCD is a little bit different, but nevertheless, you have a very strong theoretical apparatus. Standard model works. Higgs boson was, last Nobel Prize that put in some way the cherry on the tart of the standard model. But despite this precision and all the advantage of all the, let's say, precision of the standard model, there were some anomalies that were observed, years ago in the 30s. So not something really new. Like, for instance, the way how some clusters of stars, again, astronomical observation. Astronomical observation is very, very nice because you may spot phenomena that are, weird or complicated. Think about, gravitational waves now and how you can study, for instance, black holes, etc. So you see really weird stuff. The problem of gravitational, astronomical observation is that this is not as precise as a lab, as an accelerator where you have, controlled situation. So you have some guess, but at least from the point of view of observing new phenomena, this is very important. And so one, again, very simple observation was that if you think about this cluster of stars, and you may some back on the envelope calculations, you find that the strength, the gravitational force is not enough to keep them together. So you are expecting that they at some point scatter away, while they were kind of clusterized. This was an observation in 35, but then in the 70s, Vera Rubin, that is the woman that gave now the name of one of most advanced telescope. She observed that she studied more in details the rotation curves of galaxies, in particular the ones that are flat. The one that if you ask a child, please draw a galaxy, he probably do something like that, a spiral that rotate. And then again, if you do the back on the envelope calculation, you are expecting that moving from the center to the side to the end of the galaxy, you're expecting the rotation goes down with this power law. And this is completely different from what you observed. Again, the way how this was estimated is considering that the mass that is responsible for the gravitational interaction is concentrated where you have light. Okay, light means stars, and stars are usually, you can imagine sun with respect to planets, even in our small part of the universe. You have where you have stars, you have the bulk of the mass. This is also the reason why dark matter, in some sense, is showing that there is absence of light. So it's something different from the mass associated to stars. So again, this is pretty simple calculation. I mean, the astronomy made very good progress. So you could estimate, given the light that you receive, more or less how much mass you have, and then you can estimate what you are expecting in terms of gravitational force. And when you do this calculation, again, the observation is completely different. Doesn't reconcile with what you're expecting from gravitational, from the simple gravitational law. So either the gravity is completely wrong, maybe possible, and people are also working to try to see if the gravitational interaction may be, not as we are thinking. But here seems to be, a massive effect. It's not like, a small correction. This is a strong effect. So the strong effect shows or can be explained, again, maybe it's not the right explanation, but people, think about and say, let's assume now that in place of having only this light-related mass, you also have something that doesn't produce light. So it means it doesn't have light, doesn't interact with gamma, so is dark, and sit in the center of your galaxy, or actually extend over the size of where you are expecting, where you are detecting the light. Okay, so you may imagine that you have all the mass is not concentrated in the center, but is spread over a large area. Then doing this simple hypothesis, you can explain these curves. So it seems that there is something else other than the massive light-connected mass that is spread and is larger than what you're expecting. This was also confirmed by other observations. For instance, gravitational lensing. Light gets deflected by the mass. So if I look at, in principle, a star in front of me and there is something in between, in principle, I shouldn't see it. But since the space-time is distorted by the presence of a mass, if I have something massive in between, the light again can go around, and so I see it. This is called gravitational lensing. And again, from this, the effect, how much light gets deflected, again, you can estimate how much mass you have in between. And this, again, if you do the same assumption that there is only the light that you see, you doesn't match with the observation. Again, if you assume that there is something more, some more mass, not interacting with electromagnetic carriers, so gammas or photons, then you can reconcile. And given all these different observations, there's also a possibility to do some quantitative estimate of how much dark matter you need in the universe to make everything consistent. And the different observation, again, at the level of astronomical observation, they are consistent in saying, in identify a certain amount of dark matter, of matter that doesn't interact with light, okay? So there are some compelling evidence that there should be something more than the standard, let's say, stars or light-related mass. How much is it? It's huge. The problem is that, again, we are not talking about a little detail, a second-order correction. We are talking about 85% of what we have around us. I mean, based, again, on the estimate of the quantity of dark matter you have. You can estimate how much light-related mass you have, and then you do the proportion, and at the end, you find that 85% of what we have around us is totally unknown, doesn't reconcile with the mass related to stars. That is a huge effect. So it means that the standard model can only, describe a small fraction of our universe. The most part is completely, unknown. Okay? And so obviously you can imagine that given these numbers, you are in some way encouraged to study, to try to explain, to try to, all your effort should be put to understand what's this remaining 85%. We are particle physicists. There are, different way, again, to reconcile, to put all together. But let's say we are particle or nuclear physicists, and then we would like to, to think about dark matter simply as another kind of particle, another kind of, that has. We know that, for instance, leptons, they do not have hadronic interaction. Okay, they don't feel the strong force, other than using, weird effects like loops or, higher order combination. But I mean, first order, they are, completely, they do not interact. So why, I mean, we can easily think to a new kind of particle that doesn't feel the other forces that standard model describe, and maybe there is something more than what we have. Obviously, there are some constraints in this idea. We only know that dark matter should have, or at least effects are gravitational. And if we assume that is a new kind of particle maybe with a new kind of interaction, there should be, again, some facts, some effect that needs to respect, like, for instance, should be dark, should weakly interact with standard model particle, again, because if the interaction was strong, probably we would already see the effects or see the particles. And also should be consistent with other effects like CMB, the power spectrum of microwave background, should be also provide relic abundance, or how much dark matter we have. I mean, there are a couple of constraints. And obviously, it is assumed that gravity is as it is working as it is. That actually, so far, against all possible attempt to demonstrate that gravity was wrong, gravity still old. I mean, you have something that is very well established. I mean, was, for instance, gravitational waves were in some way a consequence of the gravity predicted by Einstein, I mean, years ago. So it's, it's a very strong and very robust theory. Obviously, if you now assume that you have a new kind of particles, there are mainly two ways how you can implement, you can inject in the standard model. Okay, you can think, I have a new kind of particle that interacts with with the other forces. Maybe, simply the coupling is small and then it's difficult. The interaction is small and then it's difficult to see. Or as a second step, if you doesn't find anything in this, that is, the minimal approach to modify as less as possible your baseline. So standard model works very well. So let's try to, change a little bit details of the standard model without, screwing everything up, because we know that it works. Okay, so you add a new particles that interacted through the previous, the standard interaction. Or if it doesn't work, next step is, okay, let's assume that not only we have a new kind of particle, but we may also have another kind of interaction. What about the mass of this dark matter? We are saying that this is a part. Dark matter is made by particles. What is the mass of this particle? Obviously, this is, first question. It's very difficult, because if you see here, in principle, you go from, I don't know what Z means. This is a femto electron volt, atto electron volt, I don't know Z. I don't know what this Z is, but you can imagine it is minus, so minus 9, minus 12, minus 15, minus 18, minus 21, probably. And on the other side, you go to the solar mass. You may have, this gigantic spot with very high mass particles. Obviously, having a particle with milli-electron volt, or let's say nano-electron volt, is difficult. I mean, not obvious to talk about particles. You know, the wavelength of this object will be so large, so big that is more about waves, let's say. And there is, you know, an entire field looking for dark matter in this range. The techniques you can imagine is not the one that we use in particle physics, because they are more, you know, like antennas or things that are used to detect waves rather than particles. So you know, this is a field that I'm not going to cover, but just to let you know that this is, you know, a very active field where people is investing also since there is no clue, no idea where the dark matter sits. I mean, in principle, all the entire spectrum of masses is open. To, in some way, you know, fix some ideas, we may add another couple of concepts. Again, maybe completely wrong. They are, you know, taken from, again, astrophysical observation. In some sense, it seems, you know, a reasonable assumption. First of all, that the dark matter has a thermal origin. What does it mean, thermal origin? It means that at the beginning of the universe, let's say at the Big Bang, the dark matter was in thermal equilibrium with the Standard Model. What does it mean? It means that it was interacting. Thermal equilibrium means that the particles were exchanging from Standard Model to dark matter and from dark matter to Standard Model. This allows us to draw a graph like that, an annihilation. So we have dark matter, some mediator that produces Standard Model particle, and vice versa. Okay? So if you are in connection with something, you need to have a connection. Okay? If not, it's very difficult. If we don't at least say that the dark matter is in some way connected with the Standard Model particle, it's, again, very difficult then to imagine the way how we can spot it. And the second point is that the dark matter we see today is the same amount that was left at the time of the Big Bang. Why? Cross-section is not going to change over time, because the cross-section, we are expecting that, you know, the probability of two particles of interact is not time dependent. So why we should see, we see today the same quantity of dark matter we had at the early phase of the universe, simply because the universe got expanded over time. We know that, you know, goes from a spot to something gigantic. And then the density of dark matter was not enough to let, you know, one particle of dark matter interact with another to provide some Standard Model particle. So simply, you know, it got diluted over the universe, and then most likely what we are seeing today is the leftover, what is called the thermal relic density of dark matter that we had at the very beginning. And so we can connect this kind of diagram with the quantity of dark matter that we see around us. That is a number, is really a number, a measured number. Actually, it is this number. So you can connect the cross-section multiplied by velocity of this dark matter sitting around. You can connect it to this number. And you can imagine now you have an equation. You have something that, you know, block the two things. So sigma, the cross-section, should be, or let's say sigma v should be now a number that can be connected now, because we know how to calculate this diagram. Sigma v is also proportional to the square of the mass of the dark matter and the fourth power of the mediator of the interaction. This is a standard Feynman diagram. And so you have a number here, and then you have here a combination. Here are two unknown, dark matter and mediator, but first hypothesis, we only have dark matter as a new particle, mediator is a standard one. Let's put a Z mass, for instance, okay, a Z boson. That is, you know, a weak scale, weak interaction. We say that the dark matter shouldn't interact too much, so probably order of magnitude, the interaction should reflect a similar value. Obviously, there are also some other, you know, mass constraints, again, coming from astronomical observation. Shouldn't be too low, shouldn't be too high, because if not, it's very difficult to make simulation. You know, astronomers are doing simulation of how we have the current distribution of visible mass around us. And to get something, again, reasonable, you need to have, you know, the way how forces act in a certain way. So the clusterization, for instance, gives you some limits. It cannot be too light or too, because if not, if it's too light, it never gets stay close together. So there are, you know, other limits, or in the opposite way, if the mass is too high, you get numbers that are not compatible with the rest of cosmology. So, I mean, you tend to go away. So first hypothesis is that you have these particles. Again, it is a thermal dark matter. So we are clear in mind there are these two assumptions that may be wrong, but assuming that you have this graph you think about, then you replace Z, and what happens that you get the dark matter mass in the range of 100 GeV. 100 GeV, I mean, you just plug in numbers, okay, with Z exchange or, you know, weak scale. You get that you are expecting a dark matter particles in the range of 100 GeV. Who is weighting? What's the weight of a nucleus? One nucleon is 1 GeV. 100 nucleons is 100 GeV. So we are talking about matter that is, you know, our matter that surrounds us. 100 GeV doesn't, you know, it's not something weird. It's something that we are used to. I mean, in the normal standard model particles, standard model world, we have nuclei that weight from, you know, few GeV, the proton, up to 100 of GeV. So everything, you know, it was kind of miracle. Say, okay, yes, everything match, everything makes sense. We have a Z exchange. We have a dark matter that has a mass in the range of 100 of GeV. Let's try just to optimize the way how I can spot now a GeV-like or 100 or tens or say 100 up to TeV mass particle. Then you have, you know, you need to think about the best way to detect it. But this is the, you know, the paradigm of WIMPs, the weakly interactive massive particle. And also, you know, the appealing of this approach, because you have everything, you know, almost on the table. You plug in numbers and you get something that makes sense. Obviously, depending on which particle you exchange, if you put a Z mass, is different from a Higgs mass, is different from a W mass, is different from a double Z exchange. So, I mean, you can think about a little variation, but the range, more or less, is of a dark matter made by particles that sits in the range GeV to TeV, okay? And so people optimize the way how they detect this particle. You have 100 GeV. What's the best way? Assuming that you have elastic scattering. So, I mean, forget about spin, other details. Just, you know, elastic scattering. When you have two particles we are talking about the standard mechanics because the dark matter is not ultra-relativistic. It is, you know, massive particle coming at a reasonable, you know, low speed compared to the speed of light. So if you have, you know, just a non-relativistic kinematics, and you have two particles hitting each other, what's the best way to have the maximum of energy deposition to one particle to another? You know? Think about when the two balls have the same mass. If you have a very small, think about, you know, a mosquito hitting a car. Doesn't make any difference. Two cars hitting head to head, you have, you know, a significant fraction of energy that is distributed over the two. So the best way to get the best energy deposition, how can I spot dark matter? I need to have something that is sensitive when the particle hit it. So I need to have, you know, a nucleus of a normal nucleus. Sorry, I mean a mass of a normal nucleus. That when a particle of more or less the same mass hit it, it moves. Moving, it produces ionization in the standard way. We see, you know, particles in a detector. And this is the base of this liquid argon, liquid xenon, large detector that now, reached a sensitivity, incredible sensitivity, and we are talking about tons of materials. So where you're just, exposing in a cave, well shielded by cosmic rays, you're expecting dark matter hitting them and depositing or moving the nucleus with enough strength that the nucleus in the recoil ionize, produce light, produce charge, produce something, a visible effect that is detected by your photosensor or complicated dual phase detectors of direct detection. This was the base of an entire long way. We are actually generation 2 now. I mean, its first ton size were deployed. Now we are talking about tens of tons of material, because obviously, I mean, if you don't see anything at a certain volume, you can say, okay, maybe the interaction is so weak that I need to have more material to spot something. Think about a neutrino experiment. They are using huge volume of water or whatever the scintillators, whatever you think, because the neutrino is a very small interaction. Same thing here, exactly the same. You're expecting dark matter is a weak scale interaction. You need, large size. You optimize your technology to spot that is dark matter, and this brought to, direct detection sitting in this range 1 GeV to 10 TeV, where you have a significant energy exchange. If the particles are outside this range, again, obviously there will be some energy transfer, but will be so weak that it's very difficult in a ton size detector to see something. So the technology for direct detection was exactly, optimized with the idea of measuring particles in the range, in this mass range, that unfortunately didn't show up. This is the problem. That the direct detection, these are all, let's say, exclusion limits. So you put here the cross-section, the probability that they interact, as a function of the mass of the particle. Again, this goes from, let's say, 1 GeV to 1 TeV, the range that I was mentioning. And the different experiment based mainly on this gigantic detector. There are other, tricky ways you can use, rather than using a large volume with a sizable energy exchange, you can use detectors that are, solid state, where you are looking at very, very tiny recoils. And then you can use a much, much smaller volume. So there are, the two ways of indirect detection. There are two possibilities. But the bottom line is, so far, this area is completely excluded. So it means that you cannot, I mean, if I put my detector, I don't see a dark matter signal, I cannot say that dark matter doesn't exist. I can only say that with this exposed volume, exposure time, and the quantity of material I have, the cross-section should be lower than a certain value. This is the only thing I can do. Okay, I cannot say, I cannot exclude, because if I put twice the same volume or wait twice the time, maybe I see a signal, okay? So what people does when no observation was made in a certain amount of time is to extract an upper limit. So what is the maximum dark matter interaction cross-section I would be sensitive to? And I mean, given the fact that I don't see it, means that the cross-section should be lower, assuming that I know, the efficiency of my detector and all other experimental details. This is, assume that I have it under control. So you can see here that this is excluded the region, so no observation in direct detection, despite the fact that now what you want to do is, to increase the size and really going down, 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 making a bigger detector, waiting for more time in order to spot. There are other tricks. Again, I'm just, trying to make it simple. There are other tricks. You can look at the specific area of your, because so far, I mean, these gigantic detectors are insensitive to the direction of the dark matter, while probably we know that looking at this map, or for instance, lensing and other astrophysical effect, we know where the dark matter should be. So better if I have, a well-focused telescope, dark matter telescope, better than trying to look at all the dark matter produced around. But again, assuming that you want to go down, and at some point, you're going to hit another limit, what is called neutrino floor, that, you know, in the universe, you have a lot of neutrino going around, produced because neutrino are weakly interacting, really, really weak, we know. And so at some point you have a diffuse a flux of neutrinos, and you'll never know if you see a signal in your detector, if it is given by an interaction of neutrino or given by a dark matter interaction. Again, it's not completely true, you can apply tricks, but I mean, first order, this is a kind of limit where you want to push your sensitivity, your size of your detector. If you hit the neutrino floor, that's it. I mean, you have really to invent or to apply a different approach. And on the other hand, if you look at here, the cross-section, it was excluded by, you know, again, if I just plug in numbers and they put a mass of a z, I got a cross-section in the range of 10 to the minus 39. That is excluded because all this experiment didn't see anything. Then I plug in an Higgs boson that has a larger mass, so the cross-section is smaller. And again, it was excluded almost. And then I can play with, you know, thinking about, no, it's not going to change a single boson, it's changing two bosons at the same time. This gives you, you know, a suppression factor. Okay, obviously you can complicate your theory as you like to find, you know, to match the non-observation, but this really lose part of the appeal of this simple and kind of miracle of WIMPs. And this is the reason why people diverge and say, okay, WIMPs, you know, this is a paradigm that needs to be investigated as much as we can in a reasonable way. Consider that obviously the scaling by a factor of 10 a detector is going to cost, you know, at least 10 times more. We are talking about, you know, hundreds of millions, if not billions, invested in these detectors. So, I mean, obviously there will be at some point a limit that you have to be smarter and think a different way rather than just brute force approach and scaling the size of your detector. So this is kind of, you know, not shutting the door because, again, they are still working on it, but at least justify the fact that you may think that dark matter may not be actually in that mass range. If you think about electron is half MeV, proton is 1 GeV, so I mean could be as natural as thinking the dark matter as you know, the same scale of nuclei, thinking that the dark matter has the same scale of leptons and protons, I mean particles that do not decay in the standard model, you know, they are very solid part, you know, they are the base of our universe. So why not investigate another region at lower masses that stay in, let's say, a lighter dark matter? As soon as you do this, lighter matter is, you know, well motivated, or at least it's not disfavored more than WIMPs. Obviously, it doesn't have the advantage of, you know, matching everything with a few parameters, but on the other hand, there is no reason why it shouldn't be there. The only thing that this requires, again, if you want to match the different numbers that you have, is that now you cannot invoke anymore the weak scale interaction. You really need to think about another mediator with the lighter masses with respect to the bosons we are talking about. Should be intermediate between 0 of the gamma to 100 GeV of the weak scale. You need to have a mediator that sits in between, again, to make, you know, kind of consistency of the numbers we were discussing before. So this force in some way, including or studying like dark matter, includes, or let's say force you also to include a lighter mediator. That means that we don't have a lighter mediator, so it means that you should think about a new force. So the fifth force, okay? So this is obvious again. Obviously, again, if I'm an experimentalist, so okay, it's, you know, you do whatever. You increase the number of parameters and you fit whatever you want. You add an elephant, you start with, you know, a line, and then you say, no, let's add a polynomial of 100 degrees. And then you, I mean, at the end, your curve goes through all points of the profile of an elephant. Yes. So this is the reason why, again, I just want to warn you that we are complicating the model, we are putting more parameters, and so at the end of the day, yes, you are expecting that there may be some you know, matching with observation with the reality, but the cost is not zero. You are complicated. You are inventing, and more complicated is the model. I mean, more parameter has the model, more freedom you have. That is not good, because this, at the end, you have less way to constrain and be sure that what you are inventing is correct or not if you add the parameters on parameters. Okay, so here at least you have a new mediator. New mediators brings not only the mass of the new mediator, but obviously also the way how it couples to the standard model and how the mediator couples to the dark matter. Because in the previous case, you have the weak scale, we know the coupling constant. This is the weak coupling constant, that's it. We know how it works. Now we are saying that on top of an unknown that is the mass, you also have these two vertices that are, again, two free parameters of your model. And so you see that immediately from a single parameter that was the mass of the mediator, now, or let's say, sorry, the mass of the dark matter, now you have mass of the dark matter, you have the mass of the mediator, you have the coupling of the mediator to the standard model, and the coupling of the mediator to dark matter. So you have four parameters immediately, just invoking a new theory. That makes also prediction more complicated. Anyway, you can still write something like that. I mean, the previous diagram can still hold exactly in the same way. Now, again, you have more parameters. So people, theoreticians invented, or let's say, try to visualize now in a simple way. They define this variable y that connect a fraction of these parameters. And so at the end of the day, you get the sigma v is proportional to this combination of mass of the dark matter, mass of the mediator, coupling, etc. Just, you just leave, the mass of the dark matter remain free. So if you look at how a prediction of these numbers, here, this is a number, remember, we have, a precise number for sigma v, provided by the observation of the density of the dark matter in the universe. Now you look at the epsilon is equal to sigma v multiplied by the mass square of the dark matter. And so in a plot where you have y in here and the dark matter mass in a logarithmic scale, this is power 2, but it's almost a line. So it means that now you can, in this graph, you have a line where if the dark matter is a thermal relic, and then the number I'm plugging in consistent with this hypothesis is a line. So if I found that my sensitivity in terms of this variable y that put together the mass of the mediator and the couplings is lower than that, then I have to abandon the idea of this thermal dark matter. That again can be, it may be possible that it was wrong, but it's less consistent, let's say, with my picture that I have in mind. So this is just to say that when you see plots of sensitivity, there will be lines that report about this thermal target. Thermal target means that if the dark matter, if you reach with your sensitivity of your experiment, you measure and you don't measure any dark matter lower than this value, where you're expecting that in case of a thermal dark matter you should see it, means that probably the hypothesis was wrong. And so the dark matter was not either a thermal relic, a relic from the, all the universe, or the equilibrium was wrong, and then all the castle, fall down, and then maybe you cannot even write the annihilation diagram, and then what we are talking about. It's another stuff. It's nothing to do with what we are doing, okay? This is just to explain. We will see later on how they show up in this exclusion limit and where we are in terms of sensitivity of different experiments. Okay, the way how you introduce this fifth force can be, not infinitive, because you don't want to screw up the Lagrangian with standard model. You want to add, some terms, and the number of the way you can add the new forces to the standard model is not infinitive, fortunately. So this limits the number of possibilities. Okay, you can add a scalar field, you can add a vector field, you can add a neutrino portal, what they call it, portal, or an axion. Okay, and there are mainly, these four possibilities. And clearly, having a vector portal, this is a kind you think about, electromagnetic interaction is a vector, is spin 1. So it's a kind of an extension of electromagnetic interaction. The only thing is that you don't need to, actually you need to have a photon or a dark photon that has a little bit of mass, because if it's zero mass, the interaction is going to be same as electromagnetic, that is too weak to provide the right strength. Sorry, too strong. So you need to have a kind of intermediate. So it means that your dark photon, that is an addition to the standard electromagnetic interaction we have, should have a mass, between the weak scale, 100 of GeV, and 0, that is the mass of the gamma. Again, the limit is pretty large, but at least you know where to look at. Then there are obviously other portals that are mainly in our energy range at JLab. The energy is limited. We are focusing on LiDAR matter. There are other approaches, for instance, at CERN, at LHC. The most part of researchers are focused on Higgs portal, where you have a scalar field rather than a vector field. I mean, a new mediator that is scalar rather than a vector. Again, variation, there is no phenomenology, so in principle you can take your best hypothesis and see where your energy range better matches, better cover a part of your parameter space. That again is very dangerous because you are doing the opposite. You start from what you have and try to see if it works or not, rather than doing an observation and then explain it. So it's not, let's say, correctly, let's say, justified, but this is what we have. Then another thing that you may want to think about is that, why you should have a single particle in the dark, what we call dark sector. In principle, as we have in a standard model, you have a zoology of particles. We have, how many resonances we have, how many, either if we have, 6 or a very limited number of ingredients, but the phenomenology is rich. We know very well. Hadron physics is, demonstration of that, even more than electroweak physics. So, in principle, you can think that there is not only one dark photon, there is not only one dark matter particle. There is, an entire world. Actually, being the 85% of the mass of the universe, probably is more likely is more particle than a single particle that explain everything. Anyway, so the point is that you have an entire sector that we call it hidden sector or dark sector. So something that is detached, and then you have the standard model particles. The standard model, the way how they talk each other is, there are tricks that people already apply again to extend the Lagrangian. For instance, the effective Lagrangian standard model will be, added an extra U1 group that in practice can be, translated in just having a new field that you have this chi, that is a hidden field, and coupled to the electromagnetic interaction. If you like, one possibility is to think about loops. You have a gamma on one side. Obviously, they do not talk each other, but they interact through very massive, let's say, particles. This is something that we already, we discover, for instance, the effect of the different families of neutrinos affect the mass of the Z boson, for instance. Is a way to show that you have 3 families of neutrinos, for instance. You need them because the effect of higher loop reflects in the mass. And here is something similar. There is an effective way how gamma is coupled to every photon. And so at the end, you have a connection between the hidden sector and standard model. So for what, again, this is specific for electron, but for what matters for Jefferson Lab in particular is that you are expecting to have an electron, let's say gamma rich place or electrons that has a lot of electromagnetic interaction. You produce a lot of gamma, and the idea is that some of them may transform in a dark photon, may interact, may couple to the dark photon, and then may interact with the dark matter. This is the idea. Okay, is all clear so far? This is not, not the first time we invoke a new force. For instance, for neutrino discovery at the very beginning, remember, neutron decay in proton and electron, and anti-neutrino, electronic anti-neutrino. But when they did the first measurement, they suppose, you know, it's obvious. You have a neutron is a proton and the electron put together, and then I measure the spectrum of the electron, and I see something like that. That is incompatible with the two-body decay. This requires, I mean, this is consistent with the three-body decay. And okay, we know that something was missing. You remember how difficult was also, you know, to propose to the world that the idea that there was an extra particle, a new particle. This seems to be too easy. You add another particle and everything matches, okay? This was, you know, Pauli that was scared by the idea, was just proposing, yes, you know, neutrino, maybe. It was very, very cautious and also, you know, risking to have the entire world laughing at him because he was, you know, introducing an ad hoc correction, ad hoc particle. But actually he was right. I mean, we know neutrino is there. And if you like, the way how neutrino interact with gamma-gamma interaction is nothing more than a portal in this case, actually, to be more precise, 1 minus gamma-5 interaction, that is the axial part of the interaction, is something new that was not present in for the electrons, or, you know, for the charge, for the electron charge. And again, so this kind of you know, approach is justified also by previous history. So why not now? So just to recap, we are not interested in high mass dark matter, where we leave the direct detection to be more sensitive, because these experiments are optimized to this energy mass. We want to see in a range, let's say, between 1 MeV to 1 GeV, where we can then develop, you know, the best approach, the best experimental technology to measure a possible dark matter. We know that this range is very difficult to be measured by recoil, because given the mass, I mean, as the mass is so low, the recoil of a nucleus that is 100 GeV in weight is not going to move much when a dark matter coming from the sky hit it. And on top of that, there is another problem that if you look at the characteristics of the interaction, and you have this dark matter that has no, I mean, this is a low speed, that is the one we are expecting from the sky, because if it was too, I mean, ultra-relativistics, it doesn't match with the clusterization of the dark matter itself, okay? So should be, you know, going around with a reasonable low speed. If you do this hypothesis, then you are very sensitive to the details of the interaction. If this depends on the spin and which structure the fermion, for instance, or the scalar particle you have, this is strongly dependent. If you look at here, in this mass range between 1 GeV to, let's say, it is a 1 MeV to 1 GeV, in this area, you see how if I have a scalar, an interaction with a scalar, or an interaction with a pseudo-Dirac fermion, is going to span over, you know, 20 order of magnitude. So it means that the direct detection is not only, you know, not very efficient, but the problem also is that it's very dependent on the specific structure of the particles interacting. Now, if I have, for some reason, my dark matter ultra-relativistics, everything shrinks in a very narrow band, and you get only an uncertainty of about an order of magnitude. So it means that you have much more, you know, it's much more easy to prove if the dark matter exists or not. But to have an ultra-relativistic dark matter, you need to have an accelerator. I mean, you are producing particles that when you have a lot of energy that are usually ultra-relativistics. So we can, again, in that range of masses, I mean, they shouldn't be too different from the other particles that we spot here at JLab, at CERN, etc. Okay, so when you do this assumption, and so you are producing dark matter at ultra-relativistic speed, then automatically all these differences in the interaction, whatever it is, the nature of the particles that are interacting, is going to be shrink in a very narrow band. That is, again, very appealing because I mean, you don't need, I measure here and say, okay, yes, my cross-section is less than 10 to the minus 39. Ah, okay, but what about if it is Majorana fermion? You need to go to 10 to the, okay, I do my experiment, I go down by 10 order of magnitude, say, okay, I excluded this Majorana fermion. Ah, yeah, but what about if it is, a scalar? And again, you have to play this trick again and again, while here, more or less, in an order of magnitude difference, you exclude this target. And again, this is a Y versus the mass of the dark matter, where the dependence of the specific interaction of the particle, I mean, the nature of the dark matter, if it is, again, we can imagine what we know. If it is, a fermion, it is a scalar, it is, kind of particle that is within the other, similar to the other particles. Obviously, it may be completely different, and this may, be completely wrong, but we apply what we know. And if you apply what you know, again, what we call the thermal target, so these lines sit in a region that is very close. So, I mean, at the end, if your experiment has a sensitivity that cover in this variable y 10 to the minus 15 in the whole range, you exclude it. You say, no, if my dark matter exists, is not thermal, okay? So, I mean, it's pretty appealing because it doesn't mean that you have to go down, 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 just scaling the volume of your detector or just running forever your experiment. It's saying if you reach this target, you exclude at least this thermal relic that is, pretty strong, heavy, let's say, pretty strong hypothesis, let's say, that justify in some way the whole castle. If it fall down, I mean, it's really cast, an important doubt on the entire, structure that we discussed so far. So accelerator-based experiments are gonna, explore this region. Again, nothing guaranteed that what you see at an accelerator is exactly the same dark matter you have in the sky. You see a signal, you see a dark matter signal or something unknown in your accelerator, then there will be another step to say, okay, are we sure that what I see in my accelerator is the same that is coming from the sky? But at least if you see something at the accelerator, then you have a mass, you can identify the interaction, you can identify the cross-section, and then you can easily translate to what is the limit if I have a dark matter coming from the sky, and check and cross-check and be sure that if it is the same or completely different effect, okay? So again, just this is another caveat that if you spot something at the accelerator, not automatically you can say that you discovered the dark matter, I mean the sky, the one that comes from the sky.
Maybe now is a good time for the break.
Good time for a break, yes. Oh, no, let me just another 5 minutes that I finish this, let's say, this theoretical introduction, and then, yes, and then we can move to the experimental part. Okay, this is just to give you a context, 5 minutes. So the dark photon signatures now will focus on a specific model that is assuming that we have an interaction mediated by a vector, like a mediator, so a gamma, a dark photon. And if you think about the dark photon, depending on the mass of the dark photon with respect, again, assuming that you have particles that are normal particles in the dark matter sector, simply with a different coupling, nothing special. Depending on the mass, if the dark matter mediator is heavier than the dark matter, it can decay in the dark matter. If it is lighter, it doesn't decay in the dark matter, but may decay in standard model particles, okay? So there is a hierarchy in some sense, depending on the relative mass. And the way how dark matter can be spotted, can either interact producing the mediator, like we do annihilation of E plus E minus in gamma gamma. This is exactly the same. Dark matter and anti-dark matter producing 2A prime, okay, is an annihilation process. Or you can, just mediate an interaction between dark matter and anti-dark matter producing decay into another. So this gives, again, a lot of possibilities in the experimental searches for that. Some of them will focus on having a particle of the standard model that may come from the decay of this heavy photon, or others are trying to see a signal like a neutrino in interaction that you have a dark matter particle produce and then rescatters and give you a signal in your detector. This is a completely different approach. We'll see visible and, let's say, invisible. And again, here, this is what I already mentioned. There are, a 4 parameters model where you have mass of the dark matter, mass of the mediator, coupling of the mediator to the standard model, and another coupling. And there are 4 unknowns, okay? Obviously, what you may think about is there is no reason why the coupling of the mediator to the dark matter should be weak. Order 1, I mean, order few, small, but not, why should be weak? While we know that the coupling of the A prime to the standard model particle, either quarks or leptons, should be weak. So it should be suppressed. So we are seeking or, thinking to something that goes like the charge, but that is the coupling you have in the electromagnetic interaction, but suppressed by a factor epsilon that is much less than 1. This is the reason why when we see the plot, you will see plots, exclusion plot with epsilon or epsilon squared to the square that is proportional to the number of events you see, okay? It's the charge to the second power. And again, depending on the mass of the A prime with respect, if it is visible, can decay, the lightest particle is leptons. Obviously, nothing prevents to have an A prime decaying to pions or decaying to rho or rho plus or rho minus. I mean, whatever you may think, and a combination of quarks. But let's say that, lepton seems to be a good candidate to look at the decay of an A prime in case you have a visible decay. Or you may think that, if the dark matter is lighter than the A prime, then, I mean, A prime will naturally decay in dark matter particles. Okay, so depending again on all these are completely unknown, completely invented, if you like. So we have to explore the different options. Okay, this is the last one. So in particular, now at JLab or any places where you have electron, I already mentioned that whenever you have gammas, gammas and gamma prime, they talk each other, they transform one in another. So you need to have processes where you produce a lot of gamma. And electrons is perfect because electron, every time they touch a material, it produces gammas. By Bremsstrahlung, by paired production, by many different ways. Muons are more stable, let's say. They interact much less. The lightness of the electron makes it a perfect place, perfect producer of gammas. A detector in hadron physics is a problem because this is a correction, but in this case it's good. So we need to produce gammas, and gammas are produced either by producing mesons, and you look at decay, think about the pi zero decay into gammas is a good source of pi. If you produce a lot of pi zero, is a good source of gammas. Or simply, you throw your electron or positron beam, exactly the same, through a material, possibly with high Z, and then you produce a lot of gamma, Bremsstrahlung gammas. And these gammas, some of them may produce, may radiate an A prime. So it is called H-Strahlung. I mean, the same process that you do with the standard Bremsstrahlung. With positron, you have another advantage if you start with a positron beam, that in principle, positron could also annihilate with electrons in the material, and then exactly the same as a gamma-gamma, you have E plus E minus in gamma-gamma. In this case, you may have E plus E minus in gamma-gamma, but one of the two gamma is replaced by an A1. So you have this non-resonant annihilation. Or even better, you may have E plus E minus that directly produce an A prime, or vice versa, A prime decay in A plus E minus, and so this is the time reversal process, okay? This is, we'll see that this is a very nice and smart process because in principle you have a resonance. And if you have a resonance, the kinematics is fixed. So given the energy of the two particles interacting, you can infer the mass of the mediator. While in this case, you can't. You have, you have whatever, because part of the energy can be taken by the gamma, so it's much more difficult to infer. You can only say that you see something, but it's more difficult to say what is the mass of the A prime. And on top of that, the resonant annihilation, by definition, is resonant, so it's expected to produce a peak in your cross-section, okay? And this is actually, you know, this kind of researches were applied to, for instance, Babar, Bell, Chloe, and Cleo, the experiment where you look at for E plus E minus going in one gamma, you tag one gamma, and you look at the A prime became mu plus mu minus, for instance, which, because in a collider it's much easier to measure muons. And they, you know, look for this process. You see, very simple diagram. They look for this process. Unfortunately, again, they didn't find anything. Okay, so I think we can break, and then we'll start to see over, you know, this ideas we had from the theory, how you translate now in experiments. I mean, in practical, what's the best way to. Again, this is very tricky because the ideas are, you know, very wide, and then you have to focus, you have to find the best way to do it. And you're just exploring a little stamp over, you know, a huge parameter space. But nevertheless, people, you know, spending time on that. Obviously, sorry, I didn't mention, but if there is anything unclear, anything that, you know, curiosity or whatever, something that I didn't explain, or please stop me and ask me. I'm here, okay? So don't be shy. We are, you know, this is what I understood from, so I try to transmit it to you, okay? Maybe there is something wrong also, what I understood. So please, if you have any doubt, let me know that we chat and we try to figure it out together.